Good afternoon.
Good afternoon.
All right. Well, let's see. All right. So let's see. Everyone's there in Winslow. Is everyone there? I think everyone's there in Mogollon, right?
Yeah.
All right. How about St. John's? I can't quite tell.
You
Okay. Who's not there?
no, we're all here.
Oh, okay. All right. Okay.
I like your green shirt.
Oh, thank you. Do you like, how about my tie? Do you like my tie?
Yeah, that's my favorite part.
Thank you. Okay, so let's actually back up just a little bit. So um, yesterday we didn't have class, and I didn't send any assignment, right? But last week on um, Thursday, I had asked you guys to look at some videos on Khan Academy. All right. So um, did anyone? Let's ask it this way: did anyone not do that? Did anyone not watch it? Okay.
Wait, sorry, we cut out. What did you say?
So did anyone not watch the videos on Khan Academy to do those links?
We didn't see those.
You didn't? Okay.
No.
All right. So basically, so what I'd like you to do um, is to work through those, because basically they went through the 2-4, and what I was going to do is give you credit for attending class on Thursday if you'd watched through those videos. And I don't think that they even take like probably a half hour for all of it. But anyway.
Did you send the links to Miss Lopez?
Yes.
Oh.
Yes.
She told us there wasn't.
She told us that there wasn't anything. I mean, she just left the room. She should be back in a second, but she told us there wasn't anything.
Yeah, no, there wasn't anything yesterday, but on Thursday I did send the link. So anyway, I can resend those if I need to. It's not a problem. But anyway, so and Mogollon, did you guys get the links?
Yeah, we
Okay.
did.
So did you guys watch them?
I did.
Yeah.
I
Okay. How about St. John's?
Yep, we all watched them.
Okay, so if so Denon and you ladies in Winslow, just let me know when you go through them. And what I'm gonna do is I mean it just helps your attendance grade a little bit if I just add in another day that you attended. So I want to give you that credit as if you had attended class that day. Okay.
Mr. Strong, did you get my email about Wednesday?
Yes, I did. And actually, I before I kind of want to talk to you about tomorrow. So let me just to kind of tell you, in case you're wondering what's up, because my life has been kind of turned upside down the last couple of weeks because my daughter's been in the hospital, and so I've been was going to Flagstaff every day for a while, and then now I'm going to Phoenix about every day. I drove up this morning, and I'm going to go down either tonight or tomorrow. And so I'm hoping things seem to be calmed down, but she's going to meet with her doctor tomorrow, and and I feel like I need to be there for that. So anyway, so I'm almost positive that I'm not going to be here for class tomorrow. So kind of what I thought I would do is, I mean, I could send you more links or whatever, but I kind of thought maybe what we could do is just let you take class time to do quizzes and whatever. So what do you guys think about that? Then we wouldn't have to worry about this before school, after school type thing. And we could just all do it during class time. Is that all right with everyone?
Yeah.
Sounds Gucci.
Okay, so last week we did quizzes 1-3 and 1-4. So I guess what we're on today is actually for tomorrow will be the chapter 1 test. Okay. All right. We haven't taken that yet, have we?
No, we did take the chapter
Oh, we
one.
did
test.
take the. Oh yeah, that we had the issues with that. Okay. Oh yeah. Oh, so no, we took quiz 2-1 and 2-2 last week. So now we would be looking at quiz 2-3, and then we're gonna kind of vote on quiz 2-4 because that was the material from last Thursday, and then I thought we would go over questions that you have. But if you don't, but here's what it's going to be: is that if we're not 100%, where you all feel 100% ready to do the quiz on 2-4, we'll just put that off for next week. Okay? So especially where you guys didn't get the link, so we'll see how it goes. I am going to go through the guided notes though today. So if you want to get out the notes for 2-4, and we'll just, I'm going to kind of go through it a little faster than normal, but that's okay. I mean, we'll just see how we feel about that. So, okay. And then we'll kind of vote at the end. So what I'm saying right now is no class tomorrow. And then we'll take at least quiz 2.3 and maybe 2.4 if you want. Okay. So anyway, any other questions, comments, concerns before we get started? Oh, listen. So Aiden,
Yeah.
that's not going to help you, is it?
No.
Okay. So I just realized that you're leaving early. So you wanted it like what time?
10:50 to 11:50 would be
Okay,
good.
no problem.
Yeah.
Yeah, I was thinking, oh, that will just solve everybody tomorrow, but then I realized you're leaving early. Anybody else leaving early tomorrow for sports? Okay. All right. So, okay, I'm glad I remember that. All right. So we had actually done a little bit on, just had you write down this about one-sided limits last week. And so I'm going to pick it up from there. All right. So the idea is for the limit to, oh, wait. Hold up. I forgot to share. That's where we are. That's what we wrote down last week. Okay. So the idea is that for a limit to exist, then three things must happen. The left-hand limit must exist, the right-hand limit must exist, and those two have to be equal. Okay. All right. So let's look at this first practice problem here. It says find the limit of this function as x approaches 0. Okay. So in order to determine what happens when x approaches 0, then what we're going to do is see, well, what does x approach on each side of 0? Okay. So as x approaches 0 from the left, what does this y value approach? So as x approaches 0 from the left, what is the function value?
2.
2. And then as x approaches 0 from the right, the function value is?
-2.
No,
Just 2.
it's also 2. See, as x approaches 0 from the right, we're looking at the y value. So the y value is up here at 2, not down here. The function is defined up here. So then since the left-hand limit and the right-hand limit both exist and are equal, then the limit in general as x approaches 0 is 2. Okay? So that's kind of how you use a graph. And I mean, it might seem kind of obvious, but what would be the limit as x approaches 2?
Zero.
Nope. Okay, let me say the limit as x approaches 2 from the left is 0. But I didn't say from the left or to the right. So what's the limit in general as x approaches 2?
There is no.
There isn't one.
There isn't one. It does not exist because it doesn't approach 2 from the right. Okay? All right. So now, one-sided limits have all the properties of general limits. So when we talked about adding, subtracting, multiplying, dividing, raising to a power, all those limit laws that you wrote down before also apply to one-sided limits. Okay. All right. So this is determine the limit of the function at x equals 3. All right. Here, let's call on somebody this time. All right, so Hannah Z, what's the limit of this function as x approaches 3?
2.
2. Because from the left and the right, the y value is approaching the same value, which is 2. Okay? Good. All right, now let's do the second one. All right, so Denon, what's the limit of this function as x approaches 4?
No limit.
No limit. The limit does not exist. Because, now it's not the fact that there's a hole there. It's the fact that nothing approaches 4 from the right. There's no right-hand limit. So the limit does not exist. Okay? Any questions on that? Okay, so the delta epsilon stuff that we talked about in 2.3 also applies with right hand and left hand limits. But I'm not going to get into it really again, but just know that it all applies. Okay, so now, so to prove that the limit as x approaches 2 from the right of this equals 1. Okay? So the question is, look up here in the corner here in red. Is this a true statement? Is x divided by the absolute value of x, is that equal to 1?
No.
It's
Wait,
not
yes,
al-
yes, yes.
It's not always true. But when is it true?
When it's not, when it's a positive number above 0.
Yes, when x is a positive number. Because, see, then they would be the same. A number like 5 and the absolute value of 5 is 5, and so this would be 1. But you're right, in general, you've got to be careful. Because if you have a negative, it's not going to be true. Okay, so the question here is, if you're going to simplify this and get rid of the absolute value, you have to know is x minus 2 an absolute value? Can you just drop the absolute value and have it be equal to x minus 2? So it's either going to be equal to it or it's opposite. So which would it be? Is the absolute value of x minus 2 equal to x minus 2?
No.
In general, no. But in this case, yes. Why?
Because like instead of like the v, you know, I'm having trouble explaining it, but like it'll be the same on one side of the function.
Okay. Why? What's so special about? How do I know that this is equal to that this absolute value? I can just drop the absolute value and have it be equal to 1. How do I know that for sure? And it goes back to your answer over here. When is this true?
When x is positive.
When x is positive. When x is approaching 2 from the right, is x going to be positive?
Yes.
Yes. This expression will be positive. And so the absolute value, it all has to do with what x is approaching here. Okay? So in a sense, what you can do is drop the absolute value and just get x minus 2 over x minus 2, which is 1. And so then the function minus the limit, so x minus 2 over x minus 2, that gives you 1 minus 1, which is 0. Now here it's 0 is less than x minus whatever x is approaching. So 2. So here we get 0 is less than delta. Over here we get 0 is less than epsilon. So what delta could we choose in relation to epsilon? What would we have be our answer here?
1.
So if delta, see if 0 is less than delta and 0 is less than epsilon, what we could pick is for delta to be equal to epsilon, and then those would work. So, but that's a little bit different than what we did because of this absolute value part. So the only reason why this cancels is because when x approaches 2 from the right, you can drop the absolute value and just simplify it to 1. Now, just so you know, in general, the absolute values will either simplify to, you could just drop them, or end up giving you the opposite if it's negative. Okay. Okay, so let's see. Let me. Okay, so as x approaches 0, what does 1 over x approach? How would you simplify 1 over 0? You can't divide by 0. But what would the limit be? As these values for x get closer and closer to 0. So like 0.1, 0.01, 0.001. What would 1 over a number getting smaller and smaller be?
Would it be unbounded because?
Yeah, so it's going to get bigger and bigger. So how we say that is we say that it approaches. We're gonna talk about that it approaches infinity, but for right now, we're gonna just say that limit does not exist because it goes up forever. So this is the symbol I use for does not exist, sort of the backwards E with a slash through it. And so the idea is, if you were to check it in your calculator, as the x values get smaller and smaller, the y values increase without bound, just like Nathan, I think, said. Was that Nathan? That you
Yes.
said, or eight? Okay. I want to give credit where credit's due. Okay. So doesn't exist for now. We're gonna talk more about it. Okay. So this says show that y equals cosine 1 over x has no limit as x approaches 0. So I want you to put this in your calculator. Make sure you're in radian mode. And then just take a look at it and see what you think. Okay, so you should get something like this. And as you zoom in, see, as x gets closer and closer to 0, this is one of those that doesn't have a limit because it oscillates so much. And as you zoom in, there's not a y value that you could agree on that to say as x approaches 0, the function approaches 3 or pi or something like that. It doesn't, because it keeps going up and down. Okay? And so when you get a graph like that, we say it has no limit. Okay? So from the left or the right. Now you might say, well, maybe they meet up, but you can't really show that, because as you get closer and closer to 0, it makes it you can't see the graphs. Okay. Any questions on that? Anyone not see that graph or one similar to it? Okay. Now here, just from the graph, what would you say is the limit of sine theta divided by theta as x approaches 0? From the graph. Just from one. It's 1. Now you might say, well, wait a minute, I can't plug in 0, because that'd give me a 0 in the denominator. But from the graph, you can determine that from the left and from the right, the y value is approaching 1. And so from the idea of left and right hand limits, it's okay that the function isn't defined there. The limit is still 1. Okay? So that brings up this right here, this limit that you is at the top of the last column, part 5. This limit of sine theta over theta as theta approaches 0 equals 1. That's the first limit that I'm wanting you to memorize. Okay? I want you to know that limit because it's going to come back several times in this course, in Calc 2 and Calc 3. We need to know that limit, that particular limit. And it might be the only one I have you memorize. Okay? All right? Now, you have to be careful because sometimes you'll get an evil professor that will say, what's the limit of sine theta over theta as theta approaches something else? So like if theta approaches infinity, well, as theta approaches infinity, so the x value is going out here, then it's just oscillating around 0. So the answer would be 0. But when theta is approaching 0, then the answer is 1. Okay? Now, one time we were doing a problem like this, and I said, what's the limit, or maybe it was a trig question. What's the sine of x divided by n? We had 2 variables. And a student said 6. And I'm like, how did you get 6? And they said, well, I canceled the n's and just got SIX, so 6. So anyway, that's just crazy. Okay. Let's go back. Okay, so what we're going to do is use the fact that sine theta over theta as x approaches 0 is 1. We're going to use that to simplify something like this. All right, so I have sine 2x over 2x. So what I need is whatever the coefficient of x here in the argument of the sine, whatever that is, that's what I need in the denominator. So instead of sine 2x over 5x, what I need is sine 2x over 2x, because it has to be the same thing. So what we do is we're going to multiply numerator and denominator by 2. Okay? Now, the reason we do that is, see, in the denominator, I can rearrange 5 times x times 2. I can make that, move the 2 and the 5, because multiplication is commutative. And so then the sine 2x over 2x, that's going to go to 1. And so then I have 1 times 2/5. Now that's a constant, so it doesn't matter what x is approaching. The answer is going to be 2/5. Okay? All right, so see if you can do that practice 6. All right, so Rhett, when you've got it.
3/4.
3/4, 3/4. That's right. Good job. Any questions on that? All right. Any questions on any of the notes or anything that you heard on the Khan Academy videos? Okay. All right. Well, that's it then for.
I think there's a part 6 to the notes.
Oh, is there?
Yeah.
Oh, you're right. Okay. All right. Sorry, I was looking at the wrong thing. Okay. So, here, let's. Oh well. Okay. All right. Limits involving trig functions. Sometimes we need to use trig identities to to simplify the limits. Okay? So the most common trig identity is to rewrite everything in terms of sines and cosines. Okay? That's the most common. So like with this one, okay? So you want to, so what is tangent in terms of sines and cosines?
Sine over cosine.
Sine over cosine. And what is secant?
One over cosine.
1 over cosine. Okay? So see if you can rewrite those so that it's in terms of sines and cosines, and then simplify the limit. All right, so Nathan, when you've got it, or if you get stuck, let me know.
I'm stuck. I don't know how to do this. Sorry.
Okay, no, that's all right. So you think of, so tangent t is sine t over cosine t. Secant 2t is 1 over cosine 2t. Okay? Now, why can't you just plug in 0 here?
Because you'd have a 0 in the denominator.
That's right. So is there a way that we could get rid of this t here? Because that's what's causing the 0 in the denominator. Is there a way that we can get it? I mean, nothing's going to cancel. Okay, how about the limit that we just learned? What's the limit of sine t over t?
1.
1. So you can sort of group those together and make that 1. Okay? And now you can plug in 0. So what's the cosine of 0?
One.
What's the cosine of 2 times 0? Well, it's still going to be 1. Okay, so then when you simplify all of that, you get a third times 1 times 1 times 1. So your answer is a third. Okay, so yeah, you've got to use the trig identities here, but that you always need to look out for sine of t over t, sine theta over theta. Or it could be written the other way. It could be t over sine t. It's still going to be 1. Okay? Still going to be 1. Okay. Any questions on that? Okay. All right. Well, so I'm thinking though you need more practice on 2-4. So let's just not worry about the quiz on 2-4 tomorrow. Let's just do the quiz on 2-3. Is everybody okay with that? Okay. All right. Okay. But let's go ahead and introduce 2-5. Whoops. Okay. So this next section is on what's called continuity. And you learn a little bit about this in pre-calculus. There's like 2 problems that talk about continuity and continuous. Okay. So when we plot functions based on data points, we often connect the dots to show continuity. So like if something happens like every month or whatever, we connect the dots to show that it's an ongoing process. Okay? So that's sort of like the first idea of what continuity is that if you can graph it without lifting up your pencil, then it's continuous. That's kind of the easiest definition to understand. So like here, if we're doing the distance fallen of an object over time, okay? You wouldn't just put the points here because it's not like it teleports every second to the next distance down. It keeps falling. So even at 4 seconds, we can figure out how far it's fallen and anywhere in between the points. Okay, so that's the idea of continuity. Is it the graph continues on? It's not just a series of dots. Okay, so like here, this red graph would be a continuous graph, but the blue graph is not, because see, it has a little gap there. Okay, so this is not a continuous function. All right, now here, just like we have left and right hand limits, you can talk about left and right hand continuity. But usually the only time that gets into some trickiness is with the endpoints. Okay, so like if I said, where is this graph continuous? Some of you might think from A to B, with including the endpoints A to B. Some people think, well, the graph ends and begins at A and B, so maybe let's not include those points. This is sort of a debate among mathematicians, is do you include the endpoints for continuity's sake? Okay, so I figure if mathematicians can't agree on it, then I'm not going to test you on that or even have a question based on whether you include endpoints or not. Okay. All right, so let's say if I wanted to know where is this function continuous? Well, it would be everywhere except right here at x equals 0 where there's a jump. And so you'd say, well, it's continuous from negative infinity to 0, and then up here again from 0 to infinity. So you're given the x values where it's continuous. Or you could say everywhere except x equals 0. Okay. All right, so where is this function continuous? Well, this would be continuous from negative 2 to 2. And again, you can put the endpoints or not. Okay? Doesn't matter to me. All right, so it says draw a graph that is continuous at every point except x equals 1. So you draw your own graph, and then we'll test it and see if you understand what I'm talking about here. Now, you might all have different graphs. There's not just one example. Here is one example. Just at x equals 1, the graph jumps up here. So there's a break in the graph, so that makes it discontinuous. Or if you had a hole at x equals 1, okay? All right, anyone not sure if their graph is correct? Okay, so as long as there's that, see at x equals 1, if I was graphing this, I'd have to lift up the pencil or the pen or whatever at that point, so it's not continuous. All right, so if a function f is not continuous at a point C, we say that f is discontinuous and C is a discontinuity. So just kind of some more vocabulary words here.
Mr. Strong,
Yes.
would it be okay if Skylar and I took our quiz at 11:45 tomorrow instead of during class time?
Sure. Yeah, let me make a note of that.
Okay.
11:45?
Yes.
That's okay with Ms. Lopez?
Yes.
Okay. Okay, so where is this function continuous? So put that in your calculator and see if you can figure out where is that function continuous. So 11:45 to 12:45?
Yes.
Okay. Now, I will kind of warn you is that I'm not going to be able to change that tomorrow. So like right after class, I'm going to set that up. But then, like, let's say they pop an assembly on you or something like that, you'll be stuck with that time. Okay?
Okay.
All right.
All right.
All right, so Skylar, when you've got it.
Is it -3 to 3?
Absolutely. Very good. So when you graph that, see, it's a semicircle. Now, if it looks flattened on your screen, remember zoom square is a good way to make it look a little truer. And so you could, so then it's the points are defined from -3 to +3. Okay. And you could put the brackets or the parentheses on it. All right, any questions on that? All right, what just happened? Why did it quit? Okay. Okay. All right. So the unit step function has a jump discontinuity. If a function's y value changes, here, let me switch to me. If a function's y value changes and we have to lift our pencil to graph it, it may have a discontinuity. Now you might remember that when we did the step function, then there were a lot of discontinuities because every step up would be a discontinuity. So like here's one step, and so that's what we call a jump discontinuity, is where it jumps from one y value to the next. Okay. All right, so it says draw a graph that has a jump discontinuity. So any graph that you want. All right. So you can make it as fancy as you want, but at somewhere it needs to jump up. Okay. Have a gap there where you'd have to lift your pencil. Okay. Any questions on that? Okay. Okay, so now this is kind of the big idea, the big cheese in this section here. What's called the continuity test. All right, so this is how you test to see if a point is continuous. Okay, it says a function f of x is continuous at x equals c if and only if it meets the following three conditions. Number one, the f of c exists. So it has to be, the function has to be defined at the point in question. Number two, the limit as x approaches c of the function has to exist. And then number three, the limit has to equal the function value. All right, now what I've drawn down here is examples of functions that fail different aspects of the continuity test. All right, so this first graph fails number one because it's not defined at the point C. There's just a hole in the graph there. So that fails condition number one. All right, the second graph fails condition number two, that the limit doesn't exist because the left-hand limit and the right-hand limits don't match. So it fails number two. And then this third one fails number three because the function is defined, the limit is defined, but they're not equal to each other. So this is discontinuous because it fails number three. All right, so we will pick it up from there. So again, just quizzes tomorrow. Get caught up, do some work, and then we'll hit it back again on Thursday. Okay? All right, thanks you guys for being so